There we go. So, like I said, this is one of the most important sections we'll be doing so far. And what I mean by important is, well, honestly, we've already looked at some of this stuff in lab number 4. Um, Now, in lab number 4, I had to help you with some of the questions because we hadn't done this yet. And this is something you'll see on like your final exam, where we'll look at reactions of these chemicals. Pretty easy question. I have worksheets on this that you'll see a little later, but let's get started. So, one of the main types of reactions that we're going to look at is an addition reaction. An addition reaction is exactly what it sounds like. It's when something is added to form another compound, like two or more molecules, or um, some maybe even like functional group, or some elements are added to like a carbon chain, for example. So addition reactions, literally what they sound like, we're adding molecules together to form something bigger. In terms of hydrocarbon chemistry, we're usually, or well, I guess I should say in terms of alkenes and alkynes, we're typically adding something to a double or triple bond to make it become a new chemical. And we did this in lab number 4. I know that was like a few weeks ago, but we looked at adding across a double bond things like OH, hydroxide, or something like a halogen. So addition reactions are limited to chemical compounds that have multiple bonds, so alkenes or alkynes. If you remember at the end of chapter 2, which was a long time ago now, but the end of chapter 2, we did a couple of chemical reactions, but basically we learned that, the major reaction for an alkane, for example, would be combustion. When you have an alkene or alkyne, you can have much more complicated reactions. So I'll go a little deep into the theory here, but it kind of is a lot simpler than this. When it comes to questions that you guys will need to know. So first, let's talk about, I guess, some of the theory here. The double bond of an alkene is not just a sigma bond, it also has that pi bond. Remember, last day I mentioned a sigma bond would be the simplest type of bond, usually in alkanes. But when you get alkenes and alkynes, you get this other overlapping orbital called a pi bond. The pi bond is weaker than a sigma bond. It can be broken, which means it's quite reactive. If you, I don't know if you had like Mr. John Burke or Miss Gabby, or like what instructors you've had before, but they always mention a chemical reaction is when old bonds break and new bonds form. So the reason alkenes and alkynes are so reactive is those pi bonds in a double or triple bond are weaker than a single bond. So they can be broken much easier. And when you break a bond, these carbons are looking to bond to something else. And then you can add things to it. So like things like halogens and water, or I shouldn't say water, but hydroxyl groups, OH. So one of the most simplest ones is just taking a double bond and adding hydrogen across it. So hydrogenation is what it's called. You don't need to know the names of any of these, by the way, but if I added 2 hydrogen atoms across a double bond, it would turn that alkene into an alkane. So hydrogenation of a double bond is energetically favorable. It's an easy reaction because the product is much more stable. Again, I'm going to show you pictures of this, but you don't need to know the name, but you would need to know, and we'll practice this at the end of this chapter. But if I gave you an alkene or alkyne, and you added H2, I'll explain the catalyst in a second, but let's not worry about that in a second, or let's not worry about that for now. If I have a double bond and I add H2 to that double bond, the double bond will break, and the extra electrons on the carbons, like the single now not bonded electrons, will grab onto a hydrogen each, and I'll get an alkane. So basically, if you add to an alkene hydrogen gas, you would get an alkane. That's basically the kind of summary of what's happening here. I wish like we were in class, because I kind of have an example of this. If you imagine a double bond, like your arms are folded across your chest. Maybe I'll share. I don't normally do this, but I don't know if you guys can see me here. But like if you imagine a double bond like this, two hands across each other. Imagine now if you open your arms up and you grab onto two other hydrogens like this. That's kind of what's happening. So like the double bond is breaking and it grabs onto, I can't figure out how to face my camera. It grabs onto two hydrogens, and you still have the single bond, but now the extra bond is bonded to something else. Think about the law of conservation of atoms or energy. Like these electrons aren't going anywhere. So when the bond breaks, the electrons have to do something. They have to have a reason to break. And the reason here is they grab onto the hydrogens in H2 and form an alkane. So again, in simple words, to take an alkene and turn it into an alkane, you would add hydrogen. Okay, so what about the catalyst? Okay, you guys learned about catalysts in chemistry 1121, or you should have in the electrochemistry unit. Or no, actually, you would have definitely 110% heard about catalysts in chemistry 1120 in chapter 3, your reaction rates chapter. Oh, what am I doing here? There we go. I think I might have said 1120. I mean 1121. A catalyst is a chemical that it helps a reaction happen, but isn't used up in the process. It's basically like a shortcut to make a reaction more energetically favorable. So a catalyst can sometimes be just a metal like platinum, and it helps the reaction happen. That's basically it. So sometimes a lot of these reactions, they might need a little help. You might need to add some heat. You might need to add some light. Well, in this case, we add a catalyst to help the reaction happen. So let's look at some practice here. Oh, I like these practice problems, specifically the first one. Because in the first one, I actually need to know what 1-butene is, or I can't do this. So first of all, let me just give you a little hint here. The answer to number 1 is, okay, so we have 1-butene. The answer to number 1 is 1-butane. I know that immediately because taking an alkene and adding H2 turns it into an alkane. It doesn't change anything else. It doesn't, well, and actually, I don't even know why I wrote the 1 there. It's just butane. You don't even need the 1 anymore. So the product here, and let me maybe start over. Let's draw 1-butene. So butene is 4 carbons. There's my double bond. I'm going to add H2. Now, PT is my catalyst. just like I mentioned before. So if you were doing this wink, wink, I know I turned my camera off, but wink, 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 if you were doing this on your final exam, it would look like this. And then you would just have to tell me what's the product over here. So you would say, all right, we got an alkene. I'm adding H2. The answer is butane. That's it. Just literally just remove the double bond. So again, down here, I can do the same thing. Oh, I'm not used to drawing pentane like this. This is just how the computer program did it. That's it. I mean, it does, for you guys, because this course, excuse me, doesn't go into theory very much with the reactions, you guys, it's going to take maybe a bit of memorization. But if you have a few reactions memorized, this is actually a pretty easy section. So you take an alkene, you add hydrogen, it becomes an alkane. You just get rid of that double bond. That's it. We're not going to worry about balancing or anything or side reactions or anything like that. I'm just, you tell me what happens to that hydrocarbon. That's all I need to know. All right, and we'll practice this at the end of this section so you guys can get an idea of what you really, truly need to know. Okay, so what if we get a little more complicated today? What if we add, and this is one of my favorite things. Yes, okay, I'm excited for this. I love this rule, and I love saying this guy's name. Sorry, I skipped ahead just to make sure. What if we get a little more complicated? What if we don't add H2? What if we add something like HCl or HBr, hydrogen chloride or hydrochloric acid? And you did this in the lab. I don't know if you guys remember this, but in lab number 4, this was the really stinky one. The one, I think one of your test tubes turned almost black. It can be very exothermic, adding hydrochloric acid to an alkene or a benzene ring or something like that. So, sorry. Okay, this slide has some extra words here that I don't think we really need. But anyways, we're going to look at the addition of a hydrogen halide. So in this case, we're talking about HBr to 2-butene. And the mechanism can be kind of complicated, but we can use this mechanism. The mechanism is kind of like how the chemical reaction happens. We can use this mechanism to predict, the outcome of some very complicated reactions. So what I'm saying is the way that hydrogen bromide or HBr adds to 2-butene can help us figure out how other complicated reactions happen, because when we add HBr to 2-butene, we see something very interesting happen, which is on this slide. Now, just give me 1 second. I got a message in the chat here. Oh, so the message in the chat, Naim mentioned soot. Soot is from the combustion. When we burn the hydrocarbon, the soot is typically carbon, like the carbon that's kind of left over. It could be from an incomplete combustion. So Naim, it wasn't a soot reaction where we burned it with matches. It was the reaction where you added concentrated acid, and we had a little bit more violent reaction. Okay, so back to this here. For example, again, adding HBr to 2-methylbutene. Sorry, let me fix this for 1 second here. I just want to fix, something on my slide here. Okay, just fixing the kind of the spelling of that molecule there. Okay, this is really important. So again, like I mentioned on the previous slide, understanding what's happening with this reaction will help us with other more complicated types of reactions. So hold on, something went weird there. Okay. Yeah, there we go. Everything's good. Share my screen again. So let's look at the reaction of 2-methyl-2-butene with HBr. In theory, if you think about what's happening, this double bond here, okay, it's going to break, right? That's the whole point of the reactions of alkenes and alkynes. The double bond breaks and will form new bonds with something else, right? So instead of getting two, we get one. Like that double bond here breaks and opens up to grab onto two new things. So the question is, if I have H and Br, which carbon does the hydrogen go on and which carbon does the bromine go on? So just look over to the right. In this example, I'll call this example number 1. The bromine goes on the left carbon and the hydrogen goes on the right carbon. Or in example number 2, the hydrogen would go on the left side carbon and the bromine would go on the carbon on the right. So what's interesting is when you actually do this in the lab, this is what you see on the top. You actually see the first one and you do not see the second one. So what is going on? Why does that happen? You know, when the hydrogens and the bromines try to bond to the now unoccupied electrons, or like unbonded electrons, why do they choose one carbon over the other? Well, there is a rule for that. It's a really interesting rule. Markovnikov's rule is basically one of the rules that will help us figure this out. The proton of an acid adds to the carbon in the double bond that already has the most hydrogens. So the rule is the rich get richer is a saying, is a phrase that we say in English, but the proton of an acid adds to the carbon that already has the most hydrogens. So the phrase, the rich get richer, some students use to memorize this. The hydrogen goes where there's already more hydrogens. So let me show you. Actually, okay, before I get into the kind of, no, this slide's fine. So in general, this addition to an alkene, the electrophile adds in a way to form the most stable intermediate. That's the reason. So an electrophile is basically something that accepts an electron pair to form a bond. So the chemical that's accepting the electrons here, this hydrogen, is adding to form a more stable secondary, or more stable intermediate, I'll call it. Intermediate means the reaction's not quite as done. So what happens is this double bond can break. I'm looking at the first one. Okay, and the double bond breaks and the electrons grab on to this hydrogen. Now the question is, where does the hydrogen go? On the left carbon or on the right carbon? So in the top one, example number 1, the hydrogen goes here. But what that means is this carbon now has lost its electrons. The electrons have been given to that hydrogen to form this bond here. So because this carbon is missing out on those electrons from the double bond, it's called a carbocation. It's positive. That carbocation is tertiary, meaning it's a carbon bonded to 1, 2, 3 other carbons. This is more stable. That carbon is a little bit more stable than example number 2 down here, where the hydrogen decided to go on the left carbon. So now this poor carbon is positive, it's missing electrons. And this carbon is secondary, meaning it's only bonded to 1, 2 other carbons. So the reason Markovnikov's rule happens is the intermediate, like before the reaction finishes, when the double bond breaks and grabs onto the hydrogen, it's more stable to have the carbocation, this positive carbon, as tertiary. So now, you guys are not expected to write or memorize any of this, but you are expected to know in a chemical reaction, where does the hydrogen go? So this stuff here, you don't actually have to memorize. It's not in your course objectives, but let me kind of explain why. Why is this more stable? Okay. Here's 3 different types of carbocations, or positively charged carbons. We have tertiary because it's bonded to 3 things. We have secondary because it's bonded to 2 things. And we have primary because it's only bonded to 1. So in terms of stability, it goes most stable to least stable. Stable meaning like, I hate to like humanize these chemicals, but like most comfortable, more, and again, I hate saying it, but I don't want to say happy, but it's more stable, more comfortable. It's structurally more energetically favorable, we could say. So carbocations are generally unstable because they don't have that octet rule. So the stability of carbocations here would go tertiary, secondary, primary, and then this is kind of a different example where it's not bonded to any other carbons. Oops. So the rule is an electrophile adds to a double bond to give the most stable carbocation intermediate. And an electrophile, again, is the chemical that, accepts the electron pair from that double bond. Okay, this is all really complicated, but let's actually, let me show you what you really need to know and how easy this can be. Again, this theory here, even the rule, it's not in your course outline. So the Markovnikov's rule and all this carbocation stuff, you are not expected to, you're not going to be assessed on, but it will help us understand what's happening here. So again, hydrogen is always our electrophile. It's what's accepting the electron pair from the double bond. So our question, and just ignore this stuff on the left for now, or on the right, sorry. The question is, when this double bond breaks, where does the hydrogen go? Will the hydrogen go here, or will the hydrogen go here? That's the question. That's what you guys need to know. So over here on the top, if I add the hydrogen to this carbon down here, this carbocation is bonded to 3 others. This is tertiary. Oops, I hate this pen. I know I say that every time. Okay, so this is more stable. This one is less stable. This carbon here is only bonded to 2 other carbons, so this would be secondary. Now, guys, The easiest way to remember this truly is to just remember that rule of the rich get richer. The hydrogen will go to the carbon that has more hydrogen on it. That's it. The hydrogen will always join a carbon that has the most other carbons. If there isn't a case where there's more hydrogens, it kind of doesn't matter. It'll be like 50-50. It might go on the left, it might go on the right. But that is Markovnikov's rule. If you add a HBr, HCl, HF, or HI to a double bond, the hydrogen joins the carbon with more other hydrogens, and the other element, it'll be bromine or chlorine or iodine, goes on the leftover carbon. So this is called a reaction mechanism, by the way, guys. This is a mechanism. And again, the way that this reaction happens is the double bond breaks. The electrons go with the electrophile, which is the hydrogen, and they grab onto the hydrogen. But now, because I've lost my double bond, I have a positively charged carbocation. Well, that's very convenient because the bromine that's left over that has lost its hydrogen is now negative. So the negative and the positive are attracted, and I get this compound. That's how it works. You do not need to know this. Or, well, more specifically, you do not need to draw mechanisms in this course. Again, if you were in organic chemistry at a university program and you were just doing a course called organic chemistry, you'd be drawing hundreds of these, but we don't have to. Okay, so let's practice. This is really what you need to know, or the reason why you're here today is the practice. So, okay, let's just draw each of these. So 1 pentene, 1, 2, 3, 4, 5. I'm going to add HCl, and we'll see what our product is. 2 methylpropene. Actually, maybe I'll leave that one for you. Let's try C, and I'll do C as well. So 1 methyl cyclohexene. Okay, so again, I know that was a bit confusing or a bit fast even, but this is truly what you need to know. I'm going to give you an alkene, and you're going to add HCl or HBr or HI to it and see what happens. Okay, I have 2 options here, guys. My options are, I could get this compound where the bromine goes here. Or, and don't write this down if you're following along. Well, I guess you could write this down, but you know, I'm writing one of these is the wrong answer. So the question is, where did that bromine go and where did that hydrogen go? The hydrogen joins on the carbon that has the most other hydrogens. Now, if you think about, oops, sorry guys. If you think about this molecule, 1 pentene, and you drew it like this, well, this carbon only has 1 hydrogen. This carbon would have 2 hydrogens because it's at the end of the chain. Remember, every carbon needs to have 4 things bonded to it. So this is 1 pentene. So I'll ask you guys, which molecule is correct? Which side will the hydrogen go on and which side will the bromine go on? Remember, the hydrogen will go on the side that has the most hydrogens. So in which case, sorry, did that happen? You guys let me know in the chat. I'll call one A and I'll call one B. So A and B. Where did the hydrogen, oh, so I don't know why I'm writing BR, guys. No one said anything in the chat. It's not BR, it's CL. I just have BR on the brain. thinking about hydrogen bromide from the previous example. So again, in A or B, which one had the hydrogen go to the side that had the most hydrogens? What I just heard an answer, I think. What was it?
It will be A, sir.
Yep. All right. In the voice chat, I had somebody say A. Niam in the other chat is saying A. That's absolutely correct. So it's not this one. It is this one on top. I don't feel comfortable how I explained that. Let me just show you one more time. Okay, this will be the last part of today, by the way. So 1, 2, 3, 4. Okay, so what I'm asking you guys is what happens when you add HCl to this chemical compound? Again, one easy way to think of it is if you drew the structural formula, or I'll do the condensed structural. So this compound would look like this. Okay, that would be, this is, well, like this is like kind of like a condensed structural hybrid, but this is what one pentene would look like. And the question is, I want to add HCl to this. And I'm telling you that the hydrogen, I'm going to throw this pen out the window. The hydrogen goes with the carbon with the most hydrogens. So look at my double bond here on the left. I'm going to break that double bond. Okay. And I'm going to form new bonds. Okay, so that double bond gets broken. I form new bonds. The hydrogen will go on the carbon that has the most hydrogen. So it goes on the left. That means the chlorine must go to the one on the right. So that's why the chemical compound we get looks like this. All right. Oh man, why is my pen being like this today? Anyways, my pen's sleepy, I guess. But there you go. So let me do the bottom one, and then you guys can try the top one. All right, or the middle one, and then that'll be it for today. Okay, so in this bottom one, this one's a little easier maybe. Again, the hydrogen needs to go somewhere. The hydrogen is going to go to the carbon with the most hydrogens. Now, think about this carbon right here, the top carbon. That carbon is bonded to 1, 2, 3, 4 things. That carbon, this one here, let me pick another color. Remember your magic number 4. That carbon has 0 hydrogens. That's the number 0, not OH. This carbon here, well, it's bonded to 1, 2, 3 things. I see 3 lines coming from it. So this carbon must have 1 hydrogen on it. Again, the key is to remember your magic number 4. So that means my product will be, the hydrogen is going to go to the bottom. It goes to the carbon that has the most hydrogens. So that means my double bond gets broken. You still have your methyl group here, and I'll add the iodine here. That kind of looks like a funny figure. It looks like a duck or a bird or something. But anyways, there you go. That's it. That's Markovnikov's rule. So it's 10:11, which is normally a little later than I go. So I just want to give you guys, and I know it can be hard to do, but somebody can try it. You don't have to. But I'll come back in 1 minute and we'll look at the answer to question B. All right, I'll be back in 1 minute.
Mr. Mark,
Yes?
what about the H? No need to write it in the products?
No, remember we don't write H's in skeletal formulas. So you don't need to, you do not, that's a really good question. You do not need to put H down because we never write hydrogen. I mean, you can though, like you wouldn't be wrong if you said hydrogen, but I mean, it's technically there would be two hydrogens. So you don't have to say hydrogen. All right, so guys, give question B a try, and I'll be back in 1 minute. Even if you don't share your answers with me, if you could try it on a piece of paper in front of you and just see if you get it right. And I'll be back in literally 1 minute, 60 seconds. Okay, I don't know if that was 60 seconds or not, but let's check this one out. Now, if you guys don't mind, I'm just gonna clean my slide up. Is there a way to get rid of all drawings? There must be. Erase all ink. Oh yeah. Okay, so I just wanted to clear this. Let's look at question B here completely, and then I'm done. I mean, I'm going a little long today, but this is a hard topic. But remember, all of that theory and stuff is really not as important as you guys knowing how this, like the hydrogen goes to the carbon with most hydrogens. That's really what you should take away for today. If you're more curious about this stuff, there's a lot of reading you could do, yeah, about addition reactions, but it's not in this course, unfortunately. Okay, 2-methylpropene. So propene, 1, 2, 3. 2-methyl propene. We don't really need the 1 there because no matter where you put the double bond in propene, it's going to look like that. Okay, and I want to add to that HCl. So the question is, where does that carbon go? So you could draw this if you wanted, or think about it like this. Okay, and that makes it a little easier to kind of think about where the hydrogen's going to go. The carbon on the left obviously has more hydrogens. The carbon on the right has no hydrogens. But I can already tell that just by looking at my skeletal structure. Look at the end here. Like, again, think of that magic number 4. There's a carbon here. There's a carbon here, right? The carbon has to go, or the hydrogen has to go on either the left and right carbon. Well, the carbon on the left is only bonded to 2 things. Like I can see that from my skeletal structure. So that means that this carbon must have 2 hydrogens. Remember your magic number 4. Okay, well, what about the carbon on the right? The carbon on the right is already bonded to 4 things. 1, 2, 3, 4. So the carbon on the right would have 0 hydrogens. So that means when I write my product, well, actually, let me clean that up. It'll look a little differently now in a second. This is a chemical we're all familiar with. I hate doing this, but I'm going to have to do it. The hydrogen goes here, so that means the chlorine goes here. Chlorine will go to the one with the least amount of hydrogens. Okay, so again, the hydrogen joins the most hydrogens, the chlorine joins the least hydrogens. And this makes us a chemical called tert butyl chloride, which we've seen before. Again, if you don't like that, what's happening is, I can show you on the bottom one, what's happening is this double bond is breaking and we get CH3, and then we get a compound that looks like this. Okay. So now I'm a skeletal structure person, but if you had to do this on a test and you wanted to show me this, you certainly can. But the skeletal structure would look like the guy in the top, which is a little weird looking, but that's what it looks like. So that would be tert butyl chloride. Okay, guys, a little bit longer today because it's 10:18. Again, it's a pretty interesting topic, a little complicated. Excuse me. We'll practice this a little more on Monday. I think I see you again Monday. But yeah, I mean, that's it. And we got a couple more reactions, and we'll be done chapter 3, hopefully on Monday. All right, guys, so that's it for me today. You have a fantastic weekend. There are no classes for any of you tomorrow, so I won't see you until next week. And if you have any questions, let me know. Other than that, have a great weekend, sorry.